We just got to the most exciting phase of any particle filter algorithm, the resampling phase. In my mind, this is what distinguishes the particle filter from other filters. So, what exactly is the resampling phase? Put it simply, in the resampling phase, we change the distributions of the particles according to the likelihood. So let's recap. We have n particles. Each particle has its own weight, and each weight represents its likelihood, or how close a particle is to the true state of the system. And when we do the resampling phase, we basically take all the particles, put them in one big pile, and then we draw each particle according to its likelihood. So for example, if I have 10 particles and one with a weight of just say 0.3 and another with a weight of 0.1, so the 0.3 particle will be 3 times more likely to be chosen than the particle with the 0.1 weight. So basically what it does is replace unlikely samples by more likely ones. And you can think of it like the survival of the fittest idea, that you take the most probable, the most likely particles and then move them to the next phase. And you take the least probable particles and just get rid of them, eliminate them. Why do we need to do this? 2 reasons. One, it's like a trick to avoid many samples or many particles in unlikely states or unlikely regions inside the region of interest. Sometimes there are states or there are regions that we know that we cannot be there. I don't want to waste good particles on those places. Another thing is that we need the resampling because we have a limited number of particles. We need to use them efficiently. So I want particles with low likelihood to just be eliminated. So if, for example, I have 3 particles, particle 1, P1, with the weight of 1/4, particle 2, P2, with the weight of 1/4, and particle 3 with the weight of 0.5. Okay, so basically what I'm doing is to take all the 3 particles inside the jar and just draw according to the probability. So I might get particle 3. So I get particle 3 and then I write P3. And then I take particle 3 and replace it, put it again in the jar and repeat the process. So now, for example, I get particle 2 and then I write particle 2 and I replace particle 2. And in the last phase, because I do it 3 times, I start with n particles, I end with n particles. I get, for example, another particle 3. So I started with particle 1, particle 2 and particle 3, and I end up with particle 2 and twice particle 3. So particle 3 will be more likely to move and prosper to the next phase. Why? Because its likelihood is twice as much as particle 1 and particle 2. How do we implement this resampling algorithm? Before I do it, I would like to thank Dr. Cyril Stachnes for allowing me to use his presentations. Many thanks. So there are 2 methods to do it. One is a very simple, intuitive method to understand, and the other is the more sophisticated one. So we will start with the first and then we move on to the second and we will explain in detail the second method. The first method is very easy to imagine with a roulette wheel. So let's imagine that we have a roulette wheel and each slot has a width that is proportional to the particle size or the weight size. So for example, W4, the slot of W4 is much bigger, much wider than the slot of W1 or Wn. And what I'm doing is to take a ball and spin the roulette and just look where the ball landed. Assuming the ball landed in the slot of W3, I just write W3 or P3. I just picked particle 3. and then I repeat the process n times. Now you can think of it differently as just pointing a random arrow inside this roulette and just writing down the name of the particle where the arrow is pointing. So this is the roulette resampling wheel, which is very simple to understand intuitively. What is the complexity of this algorithm? We need to repeat this process n times, so it is at least linear, and when we point the arrow to a random place, we need to deduce which particle we are actually pointing to. For example, let's say that I got the number 0.432, okay? So 0.432, which particles does it represent? So we need to search inside the particle, and you can use a binary search, which is log n, which means that the complexity of this roulette wheel algorithm is n log n. But this is not the main con. The main con is completely different, and please bear with me because it's immensely important. This method always changes the distribution of the particles. Now, most of the time it's great, but occasionally all the particles have the same weight. Why? Sometimes because we just don't get data from the sensor, and sometimes because we need or want to keep track of two different places, especially in indoor navigation problems when we have two different rooms, room number 1 and room number 3, and they are indistinguishable until you leave the room. So what basically I want to do is to maintain the probability, maintain the likelihood of room 1 and room 3. If I have like 10 particles in room 1 and 10 particles in room 3, if I'm going to use this resampling roulette wheel, so out of chance I might get more particles from room number 3, and in the next phase I will get more and more and more eventually, and this eventually occurs really fast. I will get rid or eliminate all the particles from room 1, and they will join all the particles in room 3. Therefore, I eliminated very good guesses that just out of luck. So basically, I want a method that if all the particles have the same weight, I will end up after the resampling phase with exactly the same particles. I don't want to change the distribution. How do we do it? There is a method called low variance resampling or stochastic universal resampling. And in this method, we are not just picking one particle at a time, but we are picking simultaneously n particles. Now you can think of it as like having n different arrows. Each arrow is separated 2 pi divided by n from the other, and you spin this structure of many arrows simultaneously. So when this structure lands on the roulette, you know instantaneously which particles do you need to take. I want to take this particle, and this particle, and this particle, and this particle, and this particle. So if all the particles have the same weight, this method will give me the exact same particles after the resampling phase. And now we are going to see how to implement this. First, conceptually, and then we are going to dive into the details. So let's say that I have an array of all the weights. So we have W1, W2, W3, W all the way to Wn. So basically what I'm going to do is to pick a random number between 0 and 1 divided by n. From this number, I'm going to skip by jumps of 1 divided by n. So I will take this particle, and this particle, and this particle, and this particle. And I will repeat this process n time. So by the end, I will have n new particles. So how do we implement this? Instead of looking at the weight themselves, W1, W2, all the way to Wn, we are going to look at the cumulative weight, at the CDF. So the first element in the array will be W1. the second will be the sum W1 plus W2, the third will be the sum W1 plus W2 plus W3, all the way to the last, which will be 1. Why? Because the sum of all the weights is 1. What we want to do is to draw a random number between 0 and 1 divided by n. And then we, again, just like before, we are going to skip in jumps of 1 divided by n. And basically, what we want to see if the number that we got to is bigger or smaller than the cumulative weight. So if it is smaller, I keep picking this W3, for example. So if, again, I add 1 divided by n and it is still smaller than the sum of W1 to W3, I keep picking again and again W3. If it is not, I move to the next particle and so on and so forth. Now, this method, this algorithm only has 4 lines of code. Nevertheless, it is very important that you understand it thoroughly. This low variance sampling or stochastic universal sampling is the most efficient way to resampling in a particle filter algorithm. So in the code below, you will be asked to program this method. Make sure that you understand it. It will serve you well in your next particle filter project. Good luck!